Hi there, this is Ajit. Welcome to Step by Step Data Science tutorial. So today we're in part 9, linear regression with regularization and bias variance trade-off. So today we will write linear regression with regularization equation, and we will discuss about high variance, high bias condition, and how to overcome overfitting and underfitting issues, how to write a how to draw a plot and see the learning curve of overfitting and underfitting cases. So we will discuss all these things in detail today. So let's start. This is my library. So before starting bias variance trade-off, let's see what is bias and variance. So what is bias? Bias is when we have uh, use error in both training and cross validation data set. So let's say, for example, if my data set contains price and size, and if my hypothesis gives me an output, if my model gives me an output something like this. So here we can see the module is not performing very well, and in this case we will get high training error plus high cross validation error. So if we have high training and high cross validation error, then that's the case of underfitting. This is also called underfitting, which means high bias. And if my model predicted the output something like this, so this is just right model, okay. And if my model predicted output something like this, then here we can say that this is overfitting issue, which means high variance. And here my training error is high, training error is low, but cross validation error is high. So if we have this case, then we say that we have high variance, and that's what we called as overfitting issues. So just write model means we have low bias plus low variance is what we call a good module. Okay, so this is my library, and I will show you all these cases through my code after implementing code. So this is the data set that I have used from end-to-end machine learning Coursera data course. So this is my data set, and this is my I have divided my data into training. This X is for training, this test, and then validation. So let's visualize my data first. So alt dot plot x comma y comma equal derivative rx comma is set it to 10. So we can see our data set looks something like this, and this doesn't look like a linear data set because our data set starts from 0 and till from minus 14 to 0 it's consistent, and from 0 to 40 we see drastic increase. So this data doesn't follow a linear regression line. So first we will implement a linear regression, and we will see how can we how can we fit a good module. So so this is my linear regression cost function equation. So here my cost function equation for linear regression is j of theta is 1 by 2m sigma equals 1 to m as theta of x minus y whole square plus lambda by 2m sigma theta z square 0 from 1 to n. So this term is what we call regularization. So what is regularization? Regularization is fitting the value of theta in a way that we can overcome overfitting issues. Okay, so this is how, if we add this parameter, and this parameter is termed as regularization. So regularization is needed to overcome overfitting issues. Overfitting issue by using all the available feature in our dataset. If you want to use all the features in our dataset, then we use regularization, and this will help us to overcome overfitting issue. Now we will write this equation from scratch in Python. So we will write this equation and we will test our value of theta, and then we will see high variance and high bias cases. Okay, so let's create a function. Let's create a class for linear regression. So linear regression. Okay. So my default and it will be pass. So my first function init should contain cell. So I will write first. I will write my feature normalization. So feature normalization, we know that our feature normalization, which means z score, z is x minus mu divided by sigma. So we will write this equation. So my mu will be mu equals np dot mean of x comma x is equals 0. Okay, this will be my mean. X norm will be x minus mu, and sigma will be equals to np dot std, standard deviation of x norm, making my axis as 0. Now x norm will divide this with sigma, and then we finally return x norm and mu and then sigma. Okay. Then we will write our hypothesis. So my hypothesis will be x and theta. So h will be equals to np dot product of x comma theta dot transpose. If you have any confusion in this, I have already discussed and written all this script, all this code in my last tutorial. You can view that tutorial. That's theta. Now let's write gradient descent. Self comma x comma y comma theta comma take my m equals length of x. So my equation is this. So I will write first h theta. H theta, I have already written my hypothesis. And then I will subtract with y and then do square and take sum. So my h theta, I have already written a function. This is equals to dot. So give me my h theta and my cost function. Let's say j is my cost function. So it will be h theta minus y dot transpose. So we need to take whole square of this, and then we take sum because our formula is this minus this whole square. Then we take sum. This is my sum. Then we do np dot sum divide by 2 times m. So this is my j, and my regularization term r is lambda divided by 2 times m into theta 1, which means it starts with 1 times theta 1. Now we need to take sum of this np dot sum. So my j will be equals to j plus r. So this is my cost function. Now gradient, my gradient descent equation is, this is my gradient descent equation. My gradient descent equation is 1 by m as theta of x minus y times xi. This is, then we add regularization term lambda by n theta j. So we write this equation now. So my gradient reality will be equals to np dot dot product of h theta minus y of transpose times x divided by m. Again, my here the theta j starts from 1, so I need to take from 1. So my x will be as is, my y will be starting from 1, then it will be, then I will declare of you, this will start from 1 plus lambda by m times theta 1. Okay. Return j comma that. Let's check if this is working or not. LR. Now Let's declare theta as np dot array of 1 comma 1, and my j and jd declared will be lr dot gradient descent, and I will append 1. So np dot append np dot append bracket np dot ones n comma 1, not 2 times. np dot append bracket np dot ones n comma 1, comma x comma axis is equals to 1. Then comma y comma theta comma, let's give them as 1. Okay, so my cost function is 303.99 and my gradient descent is this much. Now we will use scipy library to get optimal value of theta. Okay, so there cost of cell bracket gradient descent comma x comma y comma theta comma lambda comma max iteration is, let's say, equals 1. Let's take initial theta as dot zeros bracket x dot set of 1. First function is lambda of t such that self dot gradient descent x comma y comma t comma this equals optimizer optimize dot cost function initial theta object equals true comma equals tnc options return dot x. Okay. Now let's initiate my lambda is equals 0, say x underscore equals dot bracket dot once and comma 1 comma x is equals to 1, and my theta is zeros, okay, x underscore of dot set of 1 comma 1 and my theta is min cost dot descent comma x underscore ag comma y comma underscore. Let's check theta. Looks good. Now let's plot x comma x equals 10 purity dot x comma product of x underscore ag comma theta separated dot comma under x2. Let's include x and y label. So here we can clearly see that this is a high variance cases because the model is predicting a straight line and it's no more closer to our actual value. So this is an underfitting issue. So as per this graph, we can see this is the first case. This case we can see from this diagram. Yeah. So one thing to note is while diagnosing bias and variance, yes, so what we can say is the training error keeps on decreasing. So if we have if let's say my degree of polynomial is 1 here and degree of polynomial is 8. So for starting from 1, the training in error keeps on decreasing, keeps on decreasing, keeps on decreasing. So this is my training error, and my validation error keeps on decreasing at some point and then it keeps on increasing. Okay, so this is my cross validation error. So at this point here, so this at this point here we see high training error and high cross validation error. So here this whole area is high bias, and this area is, here we see low training error and high cross validation error. So this area is my high variance. First of all, overfitting. Overfitting. This is underfitting. Okay. So here we can clearly see that uh, this is a high bias case. So to overcome high bias case, we will add a polynomial regression. Okay, so before adding polynomial regression, we did a learning curve. So what does learning curve means? So by plotting a learning curve, we trained up our training and cross validation error. So if you run this. So this is our distribution. This is the first one is my the first one is my training error, and the second one is so so this one is so my this is my training error, and this one is validation error. So here we can see that our training error increases and validation error also keeps on increasing. Starting from first row to 12th row, our training error and validation error keeps on increasing. So here we can say that this is the pure case of high bias underfitting issue. Okay, so if we plot a learning curve here, if we check a error versus number of training example, here we see that my cross validation error and training error is consistent. So this follows something pattern like this. So if my learning curve has pattern something like this, where there's a gap in between in my training and validation error, and this gaps keeps on increasing no matter how much training data set we add. So adding training data set in this learning curve will not help. So if we have this learning curve, we can say that the model is suffering from high bias, which is underfitting issue. So here, if we do a learning plot, we can see that my training and cross validation set is consistent, and this plot shows that the model is too simple and is unable to fit our data set, resulting in high bias, sorry, which is underfitting issue. So to address underfitting issue, we add polynomial regression. Okay, so let's add a polynomial regression. I'll create a function and pole feature. Uh, So x is my input variable and p is my degree of polynomial. So x underscore equals, let's initiate with zeros. Let's say of 0, comma p for I in range of p. My x underscore will be from I, starts from I, then will be x times starts from 0 to the power of I plus 1, and then we return x. So my x new is new feature. Let's add 8 degree of polynomial x underscore. So what I did is I created a new feature, and let's say if my 0, 1, 2, 3, 4 up to 8. So for first one will be my x, second will be x, third is x times 1, x times x squared, x times cube, x times 4. So this is the polynomial degree that added. I have added new feature up to 8. So if we add this feature, then we need to normalize our data, because the power of let's say 25 to the power 4 will be really high. So we will need to normalize this feature. So for normalization, we have already created a function which calculates, we do x minus mu divided by sigma. This gives us our normalized uh, equation. So I have already written this using 8-degree polynomial. I have called feature normalization. So this is my feature. Let's give a consistent name. So I, I have written code to plot my graph and plot the learning curve. Now we will see our, if we give lambda as 100 here, if my lambda is equals to 100, then we clearly see an overfitting, underfitting issue, where we have high bias, because the model is no more close to the original input. So this is a clear high bias cases. And if we plot a learning curve, here we can see our training and cross validation error. It keeps on increasing, both are increasing. So if both are increasing, then this is plot even at one stage, it will be consistent. So training and cross validation will be consistent. So here we can clearly see a high bias cases. Yeah. So if we do lambda as 0 instead of 100, if we do lambda as 0, so this fits my line exactly, and this fits my line exactly. And if we do all the a learning curve, even if we can see uh, less value in training dataset, but extremely high value in cross validation dataset. So this is a clear example of overfitting, high bias, high variance issue. So in order to solve this issue, we need to take lambda close to 1. So if we take a lambda close to 1, click lambda 1. Then this is quite uh, it's quite fitting the module. And even if we see learning curve rate, so here we can see that the curve is decreasing. My training error and cross validation error is decreasing, and this looks a good value for choosing lambda as equals to 1. So in this case, in here we see how overfitting and underfitting in in issues is seen, and how we handle that issue by uh, by 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 using a lambda appropriate value of setting appropriate value of lambda as 1 gives us the good module. So we need to check if we have an overfitting and underfitting issue. We need to check for lambda what value of lambda will be appropriate to your module, and that will determine whether the model is not suffering from bias or variance, and model is performing well or not. So we choose lambda on that basis, and setting a value of lambda gives us the good module. Okay, so this is how we do plot linear curve, and this is how we address bias versus variance trade-off issue. I hope this video was helpful. Please like and subscribe my channel. Thank you so much.